Put your hand on the nearest solid thing. A desk, a wall, a glass of water, the skin over your own knuckles. For your senses, the world answers at once. It pushes back. It has weight. It has edges. It seems to be made of something final. But the most successful theory we have ever built says that this certainty is only the top layer. Under your hand there are atoms. Under atoms there are nuclei. Under nuclei there are quarks and gluons. And under those particles, there are fields that fill all of space. And now the uncomfortable question is not whether matter has hidden layers. It has had hidden layers every time we looked closely enough. The uncomfortable question is whether the layer we call fundamental today is only the latest surface we have mistaken for the bottom. That is the argument at the heart of modern particle physics. The familiar public story says CERN smashes particles together to look for exotic debris, and if no spectacular new particle appears, the search has failed. But the sharper story is stranger. The Large Hadron Collider is not only a machine for making new things, it is also a machine for listening to tiny disagreements. It measures masses, decay rates, lifetimes, angles, missing energy, and rare processes so precisely that even an invisible particle too heavy to be produced can leave a faint fingerprint in the data. A hidden layer does not have to walk into the detector wearing a name tag. Sometimes it only bends the numbers by a fraction of a percent. The thesis of this journey is deliberately controversial, but not careless. The Standard Model is not collapsing. It is not a failed theory. It remains the most precise description of matter that human beings have ever created. But it is also not the final story. It is too successful to ignore and too incomplete to worship. The deeper layer may not be one dramatic object waiting behind a curtain. It may be a dark sector, a new symmetry, a heavy field, a different origin of neutrino mass, or something no current model names correctly. The evidence does not prove what the hidden layer is. It proves something more unsettling. Our best theory works almost perfectly while leaving the most basic questions unanswered. That distinction matters. A weak account would say the anomalies prove new physics. A cautious account would say the anomalies may vanish. A stronger account has to hold both thoughts at once. It has to admit that many hints in particle physics have died under better data. It has to admit that the W boson, the muon, and beauty mesons have all produced moments of excitement followed by ambiguity. But it also has to ask why the theory that describes every laboratory particle so well cannot explain dark matter, cannot explain the cosmic excess of matter over antimatter, cannot naturally include neutrino masses, and cannot include gravity. If this is the bottom, it is a bottom with holes in it. To understand why that is such a strange position, we have to go back to the first mistake. For thousands of years, humans thought matter was continuous. Stone was stone. Metal was metal. Water was water. You could break these things, grind them, melt them, burn them, or mix them. But somewhere underneath there seemed to be a substance with no hidden machinery. Then the ancient atomists proposed a scandalous idea. Maybe matter was not continuous at all. Maybe it was built from tiny indivisible units moving through empty space. They had no detector, no microscope, no accelerator, only reasoning. Yet the direction of the guess was right. Matter had parts. The word atom meant uncuttable, and for a long time it carried the emotional weight of an ending. But history has a cruel sense of humor. The uncuttable thing was cut. In the 19th century, chemistry made atoms measurable. Dalton showed that elements combine in fixed ratios, as if substances were made from units with definite weights. Water always carried hydrogen and oxygen in the same proportions. Carbon dioxide always carried carbon and oxygen in a reliable ratio. The atom stopped being a philosophical possibility and became a working instrument. It explained why reactions conserved mass and why compounds formed with such precision. It looked, for a moment, like the true foundation had been found. Then electricity opened a crack. Cathode rays bent in electric and magnetic fields. J.J. Thomson showed that these rays were made of particles far lighter than atoms and carrying negative charge. The electron had been discovered. The atom, which was supposed to be indivisible, contained smaller parts. Thomson imagined a diffuse positive sphere with electrons embedded inside it, a soft model for a newly damaged certainty. It was a reasonable picture, but it did not survive the next experiment. Rutherford, Geiger, and Marsden fired alpha particles through thin gold foil and watched a few of them rebound as if they had struck something impossibly dense. The atom was mostly empty space, and nearly all its mass was packed into a tiny nucleus. That result was not merely a technical correction, it was an attack on intuition. The table under your hand does not feel empty. A wall does not feel like a cloud. A bone does not feel like a solar system, with almost all its volume removed. Yet the atom is overwhelmingly empty by volume. The sensation of solidity comes not from little hard grains pressed edge to edge, but from electromagnetic fields resisting one another. Your hand does not pass through the table because electron clouds push back. Matter feels solid because forces are arranged in a stable way, not because it is filled with tiny pebbles of ultimate substance. The nucleus then opened. Protons gave elements their identity. 1 proton meant hydrogen, 6 meant carbon, 26 meant iron, 92 meant uranium. Neutrons solved the mystery of nuclear mass and isotopes. For a while, the picture became clean again. Atoms were made of electrons, protons, and neutrons. Electrons made chemistry. Protons and neutrons made the nucleus. Maybe the bottom had simply moved one level lower. Maybe these 3 particles were the final alphabet from which the visible universe was written. But high-energy machines refused to let the story end. In the middle of the 20th century, accelerators began producing a bewildering zoo of particles: pions, kaons, lambdas, sigmas, deltas, particles that lived for fractions of a second and then decayed. A final theory should simplify the world, but the data were multiplying names faster than textbooks could organize them. The particle zoo was not a sign that nature was messy for no reason. It was the same kind of warning Rutherford had seen in the gold foil. Too many supposedly fundamental objects usually means they are not fundamental. The quark model brought order. Murray Gell-Mann and George Zweig proposed that protons, neutrons, and many of the zoo particles were made from smaller constituents. A proton became 2 up quarks and 1 down quark. A neutron became 1 up quark and 2 down quarks. Other particles became different combinations. The chaos reorganized itself into a grammar. Yet the solution created a new kind of strangeness. Quarks carry fractional electric charges, unlike anything previously observed. And no isolated quark has ever been seen. They are real, but not free. They live inside color-neutral combinations, bound by the strong force so completely that trying to separate one only creates more particles. This is where the hidden layer story stops being simple. The deeper level is not just smaller. It obeys different rules. The strong force does not behave like gravity or ordinary electromagnetism. Pull 2 electrically charged particles apart, and the force between them weakens. Pull 2 quarks apart, and the energy in the color field grows. Keep pulling, and the energy becomes enough to create a new quark-antiquark pair. The attempted escape produces new confinement. Nature does not merely hide quarks because our tools are weak. It hides them because the rules themselves forbid a lone color charge from appearing as an observable object. Then comes the reversal. At very short distances, the strong force becomes weak. This property, asymptotic freedom, allowed high-energy electrons at Stanford to reveal point-like structures inside the proton. At one scale, the quarks behave almost like free particles. At a slightly larger scale, they are imprisoned. The same force gives freedom in the smallest room and captivity at the wall. This is not intuitive physics. It is a warning that the deeper we go, the less useful everyday concepts become. We keep the word particle because we need language, but the objects are not little balls. They are excitations, fields, charges, symmetries, probabilities, and constraints. The Standard Model is the great architecture built from these discoveries. It contains quarks, leptons, gauge bosons, and the Higgs boson. It describes the strong force, the weak force, and electromagnetism. It explains why atoms bind, why nuclei decay, why the sun shines, how light interacts with matter, how particles are produced and destroyed in collisions, and why the debris from those collisions follows statistical patterns that can be predicted before the detector even sees them. It is difficult to overstate its success. In some measurements, theory and experiment agree to astonishing precision. If science were a courtroom, the Standard Model would have the strongest witness record ever assembled. And still, the very success of the model makes its gaps harder to ignore. A theory can be wrong because it fails everywhere, or it can be incomplete because it works so well in one domain that its silence outside that domain becomes unbearable. The Standard Model is the second kind. It is a palace with sealed rooms. Within the rooms it opens. The furniture is arranged with impossible accuracy. But the locked doors are not decorative. They have names: dark matter, neutrino mass, matter-antimatter asymmetry, gravity, the hierarchy of particle masses, the number of generations, the origin of the parameters. Each door says the same thing in a different language. This cannot be all. Before we enter those rooms, we need to understand the floor beneath all known particles. In modern physics, the field is more basic than the particle. An electron is not a bead moving through emptiness. It is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. A quark is an excitation of a quark field. A Higgs boson is an excitation of the Higgs field. The fields are not placed inside space like invisible fog inside a room. They are part of the structure assigned to space itself. Every point has the possibility of excitation. What we call matter is the pattern formed when fields are disturbed in discrete ways. This turns the old picture inside out. The universe is not a stage filled with tiny objects. It is a set of fields capable of carrying quantized disturbances. A particle is like a wave on an ocean, except the ocean fills all of space and the wave comes in packets. If the field is calm, we say there are no particles of that type at that location. But calm does not mean non-existent. Even a vacuum is not a blank. Quantum fields fluctuate. They jitter around their lowest possible energy. These fluctuations can produce measurable effects, such as the Casimir force between closely spaced plates and the Lamb shift in hydrogen. Empty space is not empty in the older sense. It is the quietest state of something active. Among these fields, the Higgs field is special. Most fields have a ground state whose average value is 0. The Higgs field does not. It has a non-zero value everywhere, even in empty space. Elementary particles that interact with it acquire mass. The stronger the interaction, the heavier the particle. Photons do not interact with it and remain massless. Electrons interact weakly and become light. The top quark interacts strongly and becomes enormous by particle standards. The Higgs field is not the whole source of all mass in everyday matter. Most of the mass of protons and neutrons comes from QCD energy, but without the Higgs field, the fundamental masses and the structure of atoms would not be what they are. The discovery of the Higgs boson in 2012 was therefore not just another addition to the particle list. It was evidence that the field filling the universe, the field required by the mechanism that gives elementary particles mass, is real. ATLAS and CMS saw a new particle around 125 gigaelectron volts, with properties consistent with the Higgs boson predicted by the Standard Model. For half a century, the field had lived inside equations. Then, in the debris of proton collisions, its quantum ripple appeared. It was one of the great confirmations in scientific history, but it was also a disappointment, at least for those who wanted the next revolution to arrive immediately. Many physicists hoped the Higgs would misbehave. A decay rate slightly too high, a spin assignment that did not fit, a mass value pointing clearly towards supersymmetry or compositeness. Instead, the Higgs looked frustratingly standard. Not perfectly measured, not fully exhausted, but standard enough to deny the field the dramatic clue many had hoped for. The final piece of the Standard Model fell into place, and the completed picture still did not explain the universe. This is the first real counter-argument to the hidden layer excitement. Maybe the LHC did exactly what it was built to do and found the last missing Standard Model particle. Maybe the dream of nearby new physics was wrong. Maybe nature is more economical, colder, and less generous than theorists expected. Supersymmetry did not appear in the early LHC data. Extra dimensions did not announce themselves. Microscopic black holes did not form in the detectors. Dark matter did not leave a simple missing energy excess. If one wants to be honest, the silence after the Higgs has to be taken seriously. It may mean the next layer is far beyond our reach, but the counter-argument has its own limitation. Not finding new particles at one energy scale does not prove that no hidden layer exists. It only says that certain versions of certain models with certain masses and couplings are not there. Physics has seen this pattern before. The absence of a particle in one machine becomes a constraint, not an ending. A deeper theory can hide by being heavy, weakly coupled, nearly invisible, or structured in a way that our detectors were not optimized to catch. The LHC did not close the question. It narrowed the battlefield. That is why precision has become so important. Direct discovery asks whether a new particle can be produced. Precision asks whether unknown particles or fields alter the behavior of known particles through quantum loops. In quantum field theory, a particle is never alone. It is surrounded by virtual processes, corrections, fluctuations, and contributions from every field it can interact with. The Standard Model calculates the contributions of known fields. If a hidden field exists, it may add a tiny extra correction. The particle may look normal to the eye, but its mass, magnetic moment, lifetime, or decay probability may be shifted by a small amount. The deeper layer would appear first as a decimal place that refuses to cooperate. The W boson is one of the most important tests of that idea. It carries the weak force, the force involved in radioactive decay and in the nuclear reactions that make stars shine. Its mass is not an isolated number. In the Standard Model, it is connected to the top quark, the Higgs boson, the Z boson, and the structure of electroweak symmetry. Measure it precisely enough, and you test whether the whole electroweak system is internally consistent. A hidden particle does not have to be directly visible to affect the W mass. It can enter through loops, shifting the predicted value. That is why the W became a battlefield. In 2022, the CDF collaboration at Fermilab reported an exceptionally precise W boson mass that was significantly higher than the standard model expectation and higher than other measurements. If that value had been confirmed, it would have been one of the clearest cracks ever found in the standard model. The excitement was justified. A 7 sigma discrepancy is not a casual fluctuation in the usual statistical sense. Theorists responded quickly because the result, if real, demanded new physics or a profound reassessment of the electroweak fit. Then came the discipline of the counter-argument. Other experiments did not line up with the CDF value. Atlas reported an improved value consistent with the standard model. CMS later produced a high-precision measurement that also agreed with the standard model and not with the CDF anomaly. The W boson did not simply deliver a clean verdict, it delivered a lesson. The fight is no longer only theory versus experiment. It is experiment versus experiment, systematics versus systematics, detector modeling versus detector modeling. Precision is powerful because it can reveal hidden physics. It is dangerous because it can also reveal hidden bias. That does not make the CDF result worthless. It makes it scientifically alive. A result that disagrees with others can still teach the field where the hardest uncertainties live. It forces experiments to improve calibrations, Parton distribution functions, recoil modeling, lepton energy scales, and theoretical inputs. But as a claim about a hidden layer beneath matter, the W boson currently cannot be treated as proof. The stronger, safer statement is this. The W mass controversy shows exactly how new physics might first appear, and exactly why it is so difficult to prove. The crack may close. The method remains essential. The muon tells a similar story, but with a different emotional rhythm. A muon is like a heavier electron. It has the same charge and spin, but roughly 207 times the mass. Because it is heavier, it is more sensitive to possible contributions from unknown heavy particles in the vacuum. Its magnetic moment is therefore a remarkably sensitive detector of hidden physics. The quantity called G-2 measures the small difference between a simple prediction and the real quantum-corrected behavior of the muon as a tiny magnet. For years, the muon G-2 anomaly looked like one of the most promising signs of physics beyond the standard model. Brookhaven saw a discrepancy. Fermilab repeated the experiment with greater precision, using the same storage ring moved across the country in one of the most unusual journeys in experimental physics. The Fermilab results confirmed the experimental value with increasing precision, and the final reported precision reached the level of 127 parts per billion. If the traditional theory prediction were the only theoretical answer, this would look like a major crack. But here again, the trouble lies in the word prediction. The muon's magnetic moment is easy to measure compared with how hard some of its theoretical contributions are to calculate. The electromagnetic part is exquisitely known. The weak contribution is under control. The difficult part is the strong force contribution, because low energy QCD is hard. One method uses experimental data from electron-positron annihilation into hadrons. Another uses lattice QCD, computing the quark and gluon contributions numerically from first principles. These methods have not always agreed. When some lattice-based results moved closer to the Fermilab measurement, the apparent gap between theory and experiment narrowed. This is why a careful account cannot say the muon proves new physics. It does not. The experimental number is real and impressively precise, but the theory comparison is still being refined. The strongest opposing view is that the anomaly may be a theory-side problem, not a new particle signal. That view matters because a discrepancy is only meaningful when both sides of the comparison are secure. A wrong experiment can fake a crack. A wrong calculation can fake one too. Yet, the remaining tension between methods remains as scientifically important. Even if the muon does not reveal a new particle, it is forcing physicists to understand QCD with sharper tools. Beauty mesons carry the next thread. These particles contain bottom quarks and decay in rare ways that the standard model can predict. Some of these decays test lepton universality, the idea that electrons, muons, and taus are treated identically by the weak force except for the effects of their different masses. For several years, LHCb measurements seemed to suggest that certain B meson decays produced muons and electrons at rates that did not quite match the standard model. The deviations were not individually conclusive, but they seemed to form a pattern. The idea of leptoquarks and new Z prime bosons entered the popular edge of particle physics. Then the pattern weakened. Improved LHCb analyses of key lepton universality ratios became consistent with the standard model. One of the most exciting stories in flavor physics became a cautionary tale about systematic effects, backgrounds, and how easily a 2 sigma or 3 sigma hint can grow in the imagination before the data are mature. But the entire flavor puzzle has not disappeared. Some angular observables and branching ratios still show tensions with standard model calculations. Global fits can still prefer certain beyond standard model contributions, though the evidence is far from decisive. The honest position is not triumph or dismissal. It is vigilance. These 3 stories, the W boson, the muon, and B mesons, define the controversy. One side says the standard model is holding. Every major anomaly becomes less dramatic when more data arrive. The W mystery is challenged by CMS and Atlas. The muon depends on unsettled theory. The sharpest lepton universality hints have receded. The LHC has not found superpartners, extra dimensions, or a simple dark matter particle. A skeptical physicist can reasonably argue that the hidden layer, if it exists, is not being seen in the current anomaly landscape. That is a serious objection, not a straw man. The other side says the standard model's success should not be confused with completeness. Even if every current anomaly vanished tomorrow, the theory would still leave dark matter outside. It would still leave neutrino masses unexplained in its original form. It would still fail to account for the baryon asymmetry of the universe. It would still not include quantum gravity. It would still contain unexplained parameters whose values look chosen by measurement rather than derived by principle. The absence of a clean anomaly would not make the hidden layer disappear. It would only make it harder to locate. Dark matter is the most massive silence in the room. The visible matter that builds stars, planets, gas clouds, and people accounts for only a small fraction of the cosmic inventory. Galaxies rotate as if surrounded by more mass than their stars contain. Galaxy clusters hold together and bend light as if filled with invisible gravitating material. The cosmic microwave background carries the imprint of a universe whose structure grew under the influence of a non-luminous matter component. According to the standard cosmological model, dark matter accounts for roughly a quarter of the universe's total energy density and most of its matter. Yet no standard model particle can be the dominant dark matter. This is not a tiny disagreement in a detector. It is a cosmic scale hole in the theory. If dark matter is a particle, it belongs to a sector the Standard Model does not contain. It may interact through a new force. It may be an axion, a sterile neutrino, a weakly interacting massive particle, a hidden sector state, or something even stranger. Or, if the dark matter inference is partly wrong, then gravity itself might require modification at large scales. But that path has its own severe constraints. The safe claim is not that we know what dark matter is. We do not. The safe claim is that the Standard Model does not explain the dominant gravitating matter inferred in the universe. This alone is enough to defeat any claim that particle physics is finished. A theory of matter that leaves most matter outside its particle list cannot be final in a cosmic sense. It may remain perfectly accurate for collider processes and atomic physics while still being incomplete as a description of the universe. That is the subtlety. The Standard Model is not wrong the way an old map of a flat Earth is wrong. It is incomplete the way a street map is incomplete if you ask it to explain weather, geology, and the hidden plumbing beneath the city. It was built for one domain and performs there with brilliance. The cosmos asks questions beyond that domain. The matter-antimatter asymmetry is another locked door. The known laws almost treat matter and antimatter symmetrically. The Big Bang should have produced them in nearly equal amounts. Matter and antimatter annihilate when they meet, producing radiation. If the early universe had made exactly equal amounts, almost everything would have vanished into light, leaving no stars, no planets, no bodies, no listeners. Yet matter survived. The asymmetry had to be tiny, perhaps one extra matter particle for every enormous number of matter-antimatter pairs, but that tiny excess became everything. The Standard Model contains CP violation, but not enough of it to explain the observed imbalance. This is not a poetic problem. It is a physical inventory problem. We exist because the early universe chose matter over antimatter by a small amount. The Standard Model knows how to violate the symmetry in certain processes, but the strength and structure of that violation appear insufficient. That points toward additional CP violation, perhaps in neutrinos, perhaps in a high-energy sector we cannot directly access, perhaps in interactions that occurred when the universe was far hotter than any accelerator can recreate. The hidden layer may not be hidden because it is spatially small. It may be hidden because it operated in the first fractions of a second of cosmic history and left only matter itself as evidence. Neutrinos deepen the problem. In the original Standard Model, neutrinos were massless, but experiments showed that neutrinos oscillate, changing flavor as they travel. Oscillation requires mass. The masses are extremely small compared with the charged leptons, and the pattern of mixing is unlike the quark sector. The Standard Model can be extended to include neutrino masses, but the extension raises new questions. Are neutrinos their own antiparticles? Is their small mass caused by a seesaw mechanism involving extremely heavy right-handed neutrinos? Could those heavy states have helped generate the matter-antimatter asymmetry in the early universe? The neutrino, almost invisible, may be one of the cleanest doors to the hidden layer. Gravity is the largest missing piece, but it behaves differently from the others. The Standard Model is a quantum theory. General relativity is a classical theory of space-time geometry. Each works magnificently in its own regime. Put them together in the most direct way, and the mathematics breaks. The infinities do not renormalize as they do in the other interactions. Black holes, the Big Bang, and perhaps the interior of space-time itself demand a quantum theory of gravity. But the standard model does not provide it. The hidden layer beneath matter may therefore be connected not only to new particles, but to the nature of space-time. Here the debate becomes more philosophical but still grounded. One view says particle physics should focus on reachable experiments, precision Higgs measurements, rare decays, dark matter searches, neutrino oscillations, proton decay, and collider anomalies. Another view says the real hidden layer may lie so far above accessible energies, perhaps near the Planck scale, that no collider will ever touch it directly. If so, the best we can hope for are indirect fingerprints, symmetry patterns, rare forbidden processes, cosmological relics, or mathematical consistency. This is a hard truth. The universe is not obligated to place its deepest secrets within our budget or our engineering limits. So what could the hidden layer be? Supersymmetry was once the favored answer for many theorists. It proposes that every known particle has a partner with different spin. Fermions paired with bosons, bosons with fermions. It can help stabilize the Higgs mass, improve the unification of forces, and provide dark matter candidates. It is elegant in a way that makes physicists listen. But the simplest, most accessible forms of supersymmetry have been cornered by the LHC's null results. If superpartners exist, many must be heavier, more compressed in mass, more weakly produced, or hidden in more difficult signatures than many early models expected. This is where the controversy around supersymmetry becomes a lesson about beauty. A theory can be mathematically beautiful and still not be realized at the scale we hoped. The fact that supersymmetry solves certain theoretical problems does not force nature to use it in a discoverable way. But the absence of superpartners at the LHC does not disprove all supersymmetry either. It changes the price. It makes the theory less simple, less immediately natural, less satisfying to some. The hidden layer may still be supersymmetric, but if it is, it has been more evasive than many expected. Composite Higgs theories offer another possibility. Maybe the Higgs boson is not elementary. Maybe it is made of more fundamental constituents bound by a new force, just as protons and neutrons are made of quarks bound by QCD. The public story of the Higgs often treats it as the final particle, the last tile placed in the standard model mosaic. A composite Higgs would turn that story inside out. The particle that seemed to complete the model would become the first sign of another layer beneath it. Its interactions would deviate slightly from standard model predictions. Its self-coupling might reveal a deeper structure. Precision Higgs physics is therefore not a ceremonial victory lap. It is a search for seams. Extra dimensions are a different kind of hiddenness. They do not say there are more particles inside known particles. They say the stage itself may have more directions than we experience. Some theories curl extra dimensions so tightly that ordinary matter cannot move through them. Others place our universe on a brain inside a higher dimensional bulk. In certain models, gravity appears weak because it spreads into extra dimensions while the other forces remain confined. The LHC has searched for signs of such dimensions, including missing energy, resonances, and exotic phenomena. No confirmed signal has appeared, but the idea remains a reminder that the hidden layer may not be below matter in a simple spatial sense. It may be orthogonal to our entire way of seeing space. Dark sectors may be the most conservative hidden layer idea in one sense and the most radical in another. We already know from cosmology that something dark gravitates. It may be that dark matter is not a single lonely particle. It may live in a sector with its own forces, its own particles, perhaps even its own complexity, interacting with us only through gravity or through very weak portals, such as the Higgs portal, kinetic mixing, or neutrino mixing. If so, the standard model would be one island in a larger archipelago of fields. Ordinary matter would not be the main substance of the universe. It would be the visible coastline. This possibility changes the emotional meaning of collider searches. When a detector records missing transverse energy, it is not just looking for an accounting error. It is asking whether energy has left the visible sector. It is asking whether, for a fraction of a trillionth of a second, the collision opened a door into particles that do not leave tracks, do not light up calorimeters, and do not talk to photons. Most such events have standard model explanations involving neutrinos or detector effects. But the method remains one of the few ways we can ask the dark universe whether it has microscopic structure. There is also the possibility that the hidden layer is not a new particle at all, but a new principle. The standard model contains patterns it does not explain. 3 generations, strange mass hierarchies, mixing angles, charge assignments, the near convergence of force strengths at high energy, the smallness of neutrino masses, the stability or metastability of the Higgs vacuum. These may not be clues pointing to one new particle. They may be shadows of a deeper symmetry, a high-energy boundary condition, a selection effect, or a mathematical structure we do not yet know how to test. Sometimes the next layer is not a brick under a brick. Sometimes it is the rule that explains why the bricks exist. This is where the public imagination often becomes impatient. It wants a reveal, a fifth force, a new particle, a headline saying the standard model has been broken. But science at this edge rarely works like a movie. It works through pressure. A ratio refuses to be one. A mass sits slightly high. A decay angle leans away from prediction. A cosmological abundance cannot be built from known ingredients. A neutrino changes identity in flight. A detector sees nothing where a beautiful theory expected something. Each pressure point is ambiguous alone. Together, they form the shape of ignorance. The Large Hadron Collider, meanwhile, is changing. The machine that discovered the Higgs has entered a long transformation toward the high luminosity LHC. The goal is not simply to collide particles at higher energy, but to produce vastly more collisions. More luminosity means more data. More data means access to rarer processes, smaller deviations, better Higgs measurements, and improved sensitivity to subtle new physics. The upgraded machine is expected to produce hundreds of millions of Higgs bosons over its lifetime. If the Higgs is a portal, a composite object, or a field influenced by hidden sectors, precision may expose it. This future is less cinematic than a single discovery announcement, but it may be more powerful. The Higgs self-coupling, for example, is tied to the shape of the Higgs potential. That shape matters for understanding electroweak symmetry breaking and the stability of the vacuum. Measuring it is extremely difficult because producing pairs of Higgs bosons is rare, but the measurement is one of the most direct ways to ask whether the field that gives elementary particles mass behaves exactly as the standard model says. A deviation would not be decoration. It would be a structural clue about the field that fills the universe. Beyond the high luminosity LHC, physicists are debating future machines. A future circular collider at CERN would place a new ring roughly 91 kilometers around beneath the region near Geneva. First, as an electron-positron precision machine, and later, possibly, as a much higher energy proton collider. Other proposals include linear colliders and circular Higgs factories elsewhere. These projects are expensive, technically demanding, politically difficult, and scientifically controversial. The strongest argument against them is not anti-science. It is that the next layer may be too far away, and that building larger machines without a guaranteed target may not be the wisest use of resources. That counterargument deserves respect. A future collider is not a magic key. It might measure the Higgs exquisitely and still find no deviation. It might push direct searches to higher masses and still find no new particle. The public should not be told that a larger machine guarantees a revolution. It does not. But the opposing view has a limitation too. If we only build instruments when discovery is guaranteed, we misunderstand how discovery works. The electron was not guaranteed. The nucleus was not guaranteed. Quarks were not guaranteed. The Higgs was predicted, but its mass and behavior were not fully known. New instruments do not buy certainty. They buy access. The deeper question is, what kind of access the next era needs? Higher energy can produce heavier particles directly. Higher luminosity can reveal rarer processes. Cleaner electron-positron collisions can measure known particles with less background. Underground detectors can watch for proton decay and neutrino behavior. Direct dark matter experiments can listen for the faintest recoil in ultra-cold targets. Astrophysical surveys can map the distribution of invisible mass and the expansion history of the universe. No single machine owns the hidden layer. If it is real, it may require an alliance of colliders, cosmology, neutrino experiments, gravitational observations, and precision atomic physics. That is why the phrase hidden layer should not be taken too literally. The next reality may not be a smaller set of beads inside quarks. It may be a network of fields that couple weakly to ours. It may be a high-energy symmetry broken so early that only relics remain. It may be a topological structure. It may be a quantum gravitational principle. It may be a dark sector with its own history. Or it may be that several of these ideas are partially right, and none of them is the whole answer. Nature is not required to respect our categories. But whatever the answer is, one lesson is already clear. Matter has never been what it first appeared to be. The old intuition says the world is built from solid pieces. Physics says solidity is emergent. The old intuition says empty space is nothing. Physics says the vacuum is filled with fields and fluctuations. The old intuition says mass is an inherent weight carried by tiny objects. Physics says mass can arise from interaction with the Higgs field and from bound energy in the strong force. The old intuition says a completed particle list would be an ending. Physics says a completed list can be the beginning of a deeper problem. There is a strange humility in this. The Standard Model tells us that the matter in your body is not a collection of miniature stones. It is a pattern of field excitations stabilized by symmetries and interactions. The carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron in your hemoglobin, all trace their behavior to a small set of fields and forces. The world of color, sound, breath, muscle, memory, and fear emerges from quantum rules that fit on pages of equations and yet require enormous machines to test. That is already astonishing, even before we add the next layer. And if there is a hidden layer, it is not separate from you. It is not somewhere out beyond the galaxies. It would be inside every atom you have ever touched. If dark matter has a portal to ordinary matter, the portal is a field that passes through you now. If neutrinos owe their masses to a heavy sector, your existence depends on a cosmic asymmetry that may have been produced by particles long gone. If the Higgs is composite, every electron mass in your body is tied to a deeper binding structure. If supersymmetry exists at high scales, the vacuum around you carries traces of a symmetry too heavy for direct sight. The deepest physics is never merely far away, it is also under your skin. This is where the story becomes more intimate than any machine at CERN. You are not built on certainty. You are built on a theory that works beautifully and a mystery that remains open. Every atom in your body is explained well enough for chemistry, biology, medicine, and technology to exist. Yet the cosmic inventory says most matter is invisible. The neutrino says the original model was incomplete. The early universe says matter survived for a reason we have not fully found. Gravity says space-time still resists quantization. Precision measurements say, maybe, something is tugging at the edges. The world is reliable enough to live in, and unfinished enough to haunt us. A bad version of this story would end by promising that CERN is about to reveal the final secret. That would be dishonest. The next data may close some anomalies. The next measurements may strengthen the standard model further. The hidden layer may remain hidden for decades. Some beautiful theories may die. Some popular hopes may fade. But a better ending does not need false certainty. The better ending is this. The search itself has become sharper. We now know where the standard model is strongest, where it is silent, where it is stressed, and where the next generation of experiments must press. Imagine the detector when the beams return in their upgraded form. Protons circulating underground at nearly light speed. Superconducting magnets colder than deep space. Millions of sensors waiting in darkness. Most collisions will produce ordinary debris, familiar patterns, events that confirm what is already known. But science advances because ordinary is measured so carefully that the abnormal cannot hide forever. A rare Higgs pair, a forbidden decay, a missing energy pattern, a neutrino behavior, a proton that should be stable but is not, a decimal place that refuses the theory. Any one of these could be the first clear sign that the layer beneath the standard model has finally touched the surface. Until then, we live in the tension. The standard model is complete, and it is incomplete. The Higgs was found, and it did not answer everything. The anomalies are exciting, and many may disappear. The hidden layer is not proven, and yet the known universe insists on something beyond the known list. This tension is not a weakness of physics. It is the engine of physics. A theory earns trust by surviving tests. It earns its successor by revealing the questions it cannot answer. There is another reason the search has become so difficult. The standard model is not a single loose idea that can be easily overturned by one surprising plot. It is a network of linked measurements. Change one part, and the change echoes through the whole structure. If a new particle shifts the W boson mass, it may also shift the decay of the Z boson, the behavior of the Higgs, the magnetic moment of the muon, or the rates of rare flavor processes. A proposed solution to one anomaly has to survive every other measurement that already agrees with the standard model. That is why beyond standard model physics is hard. The new layer must be strong enough to leave a trace, but weak enough not to ruin everything that already works. This constraint is not a technical inconvenience. It is the central drama. Nature has left very little room for simple answers. A new force cannot simply appear at ordinary energies because atoms, chemistry, nuclear processes, and precision electroweak data would already have noticed it. A new particle cannot couple strongly to electrons, quarks, or photons across a broad mass range without showing up in collider data or astrophysical observations. A dark particle that explains galaxies must avoid being seen in underground detectors, collider missing energy searches, cosmic rays, and the cosmic microwave background. The hidden layer, if it exists, has survived a century of increasingly aggressive interrogation. That means it is either subtle, remote, or disguised by a principle we do not yet understand. This is why the idea of effective field theory has become so important. An effective theory does not claim to be final. It claims to be accurate at a certain range of energies and distances. Newtonian mechanics is an effective theory for slow objects and weak gravity. It fails near light speed and strong space-time curvature, but within its domain it remains extraordinarily useful. The Standard Model may be an effective field theory of the known particles at accessible energies. New physics could live at higher energies and still leave suppressed traces at low energies. Those traces appear as higher dimensional operators, tiny corrections to interactions that the Standard Model treats as complete. This way of thinking makes the hidden layer less cinematic but more precise. You do not need to know the full high-energy theory to describe its low-energy fingerprints. You can write down every possible correction allowed by the known symmetries and ask experiments how large those corrections can be. If the coefficients are zero within uncertainty, the hidden scale is pushed higher. If a coefficient refuses to be zero, the hidden layer gains a direction. This is not as emotionally satisfying as discovering one new particle, but it is one of the most disciplined ways to search. It turns ignorance into a measurable space. The Higgs sector is especially important in this language because the Higgs is not just another particle. It is a field with a non-zero value in the vacuum. It touches the mechanism by which elementary particles acquire mass. It is a scalar field, and scalar fields are unusually sensitive to high-energy physics. That sensitivity is what creates the hierarchy problem. Quantum corrections should, in a naive calculation, push the Higgs mass toward extremely high values unless something cancels them or explains why they remain small. The observed Higgs mass is not impossible inside the Standard Model, but many physicists regard it as unnatural in a technical sense. This discomfort is not proof of new physics. It is a clue about what kind of answer theorists expected nature to provide. Naturalness has become one of the most controversial words in modern physics. For decades, it guided expectations. It suggested that if a parameter looks finely balanced, there should be a mechanism that makes it stable. This logic worked before. It helped motivate ideas that successfully predicted new phenomena in earlier eras. But the LHC has challenged the confidence of naturalness. If the Higgs mass is protected by accessible new particles, why have those particles not appeared? One answer is that they are heavier than expected. Another is that they interact in more hidden ways. A harder answer is that naturalness, at least in its simplest form, may not be a reliable guide. That possibility is deeply uncomfortable for theorists. If nature does not care about our sense of naturalness, then some of the strongest aesthetic arguments for nearby new physics weaken. The universe may simply contain parameters that look strange to us because we do not know the full statistical or cosmological context. The multiverse is sometimes invoked here, not as a proven solution, but as a possible explanation for why certain constants take life-permitting values without a dynamical mechanism forcing them. This idea is controversial because it can seem to weaken the predictive power of physics. If too many things are explained by environmental selection, the theory risks becoming harder to test, and yet dismissing naturalness entirely would be premature. The history of physics shows that apparent coincidences often point to hidden structure. The periodic table looked like a pattern before quantum mechanics explained electron shells. The particle zoo looked like a pattern before quarks explained hadrons. The near unification of couplings may be a pattern. The generational structure of fermions may be a pattern. the smallness of neutrino masses, may be a pattern. The Higgs mass may be a pattern. The problem is that some patterns are real and some are mirages. Science advances by learning which is which. The three generations of particles are one of the strangest unresolved patterns. Ordinary matter uses only the first generation, up quarks, down quarks, electrons, and electron neutrinos. The second and third generations are heavier echoes. The muon is an electron with more mass and a short life. The tau is heavier still. Charm, strange, top and bottom quarks appear in high-energy events and quickly decay. They do not build chairs, planets, or bodies. Yet without at least three generations, the Standard Model's CP violation structure would be very different, and the universe's history might not allow the matter imbalance we observe. Nature seems to have installed extra copies of matter for reasons we still do not fully understand. The top quark makes this mystery sharper. It is so heavy that it has about the mass of a gold atom concentrated in a fundamental particle. It couples to the Higgs field more strongly than any other known particle. Because of that, it plays an outsized role in quantum corrections to the Higgs sector and in the question of vacuum stability. A small change in the top mass or Higgs mass can alter conclusions about whether the electroweak vacuum is absolutely stable or metastable. This does not mean the universe is about to decay. If the vacuum is metastable, its lifetime appears vastly longer than the current age of the universe. But it means the measured values of known particles place our universe near a boundary in theory space. That is not proof of design or destiny. It is a strange fact. Vacuum stability is one of those topics that easily becomes exaggerated. A careless version says the Higgs could destroy the universe at any moment. A careful version says the shape of the Higgs potential, combined with the top quark mass and other Standard Model parameters, suggests that our vacuum may be stable or metastable, depending on precise values and assumptions. The difference matters. Metastable does not mean fragile in the everyday sense. It means the current vacuum may not be the lowest possible energy state, but the probability of tunneling may be fantastically small. The science is not a doomsday prophecy. It is a measurement of how the fields beneath matter arrange their lowest energy possibilities. The electron also deserves respect in this story. It appears simple, point-like down to current limits, and stable. Its magnetic moment has been measured and predicted with extraordinary precision, making it one of the greatest triumphs of quantum electrodynamics. If the electron had shown a large anomaly, new physics would have been difficult to hide. But it has not. That stability and agreement constrain many speculative models. Any hidden layer that couples strongly to electrons must pass through the narrow gate of electron precision data. The electron is small, but it is one of the strictest guards at the entrance to new physics. The proton, by contrast, is not elementary, but its stability may be a window to grand unification. If a grand unified force connects quarks and leptons, protons should eventually decay. The expected lifetime in many models is so enormous that a single proton is useless as a detector. So experiments watch vast numbers of protons inside huge tanks of water or other materials, waiting for a decay pattern that should almost never happen. The silence so far has ruled out simple, grand, unified models and pushed possible lifetimes higher. But the method remains profound. A proton decay event would not merely discover a rare process. It would show that matter itself is not permanent in the way ordinary chemistry assumes. Think about the emotional reversal in that. The proton is the center of ordinary matter. Hydrogen is one proton and one electron. Stars burn hydrogen. Water contains hydrogen. Organic chemistry depends on hydrogen. If protons decay, then the long-term future of matter changes completely. Atoms become temporary arrangements on a timescale far beyond stars. The hidden layer would not be a small addition to physics, it would be a new mortality written into the heart of matter. No proton decay has been seen. And the safe conclusion is restraint. But the search is one of the cleanest ways to test whether quarks and leptons are truly separate families or two faces of a deeper unity. Neutrino experiments approach the same mystery from the opposite side. Neutrinos barely interact, yet they cross the universe in enormous numbers. Trillions pass through your body every second, almost all without touching a single atom. Their oscillations reveal that they have mass and that flavor is not fixed. Long baseline experiments send beams of neutrinos through hundreds or thousands of kilometers of Earth, watching how they change identity. Solar, atmospheric, reactor, and accelerator neutrino data together form a map of a sector that the original Standard Model did not contain. If neutrinos violate CP symmetry strongly enough, they may help explain why matter survived the early universe. The next generation of neutrino experiments, such as DUNE and Hypercameo-Candé, will not simply refine a number. They will ask whether neutrinos and antineutrinos oscillate differently. They will search for mass ordering, rare processes, and possible signs that neutrinos are Majorana particles. If neutrino-less double-beta decay is observed, it would mean lepton number is not conserved in the expected way, and that neutrinos may be their own antiparticles. That would be beyond Standard Model physics of a very deep kind. It would connect the smallest masses we know to the largest question of why the universe contains matter at all. Meanwhile, dark matter searches continue on multiple fronts because no single strategy can cover the possibilities. Underground detectors look for nuclear recoils caused by dark matter particles passing through Earth. Axion experiments look for conversions between axions and photons in strong magnetic fields. Colliders look for missing energy. Telescopes look for annihilation or decay products in space. Precision cosmology maps how structure formed under the gravitational influence of invisible matter. Each method has found constraints rather than confirmation. This might seem discouraging, but constraints are not empty. They carve away bad ideas and force better ones. One possibility is that dark matter is not a thermal relic of the kind once expected. It may be ultralight, behaving more like a field spread across galaxies than a swarm of heavy particles. It may be primordial black holes, though constraints make that difficult for all of dark matter. It may be asymmetric, with a matter-antimatter imbalance in the dark sector mirroring our own. It may interact with itself in ways that help explain small-scale structure. The word dark matter may be hiding a whole ecosystem of ideas. We should not let the simplicity of the phrase make the phenomenon seem simple. There is a philosophical danger here too. When a subject has many possible explanations, it is tempting to make the mystery sound like evidence for one's favorite theory. But a mystery is not a measurement of your preferred answer. Dark matter proves that something is missing from the Standard Model or from our gravitational description at cosmic scales. It does not by itself prove supersymmetry, axions, sterile neutrinos, modified gravity, or any specific dark sector. A responsible controversial account must keep the pressure without pretending the verdict is in. The pressure is real. The verdict is not. The same caution applies to collider anomalies. A 2 sigma deviation is not a discovery. A 3 sigma deviation is not a discovery. Even a 5 sigma result can be complicated if systematic errors are not fully understood or if other experiments disagree. Particle physics uses high thresholds because the data are enormous, and the ways to fool yourself are numerous. When millions or billions of events are analyzed through many channels, some fluctuation somewhere is expected. The discipline of the field is not only in finding excesses, it is in surviving the temptation to love them too early. This discipline can frustrate the public because it makes science sound hesitant. But hesitation is not weakness at the frontier. It is the method that prevents imagination from outrunning evidence. The stronger the claim, the more severe the check. If someone says a hidden layer has been found, the questions come immediately. What is the significance? What are the systematic uncertainties? Is there an independent confirmation? Does it appear in related channels? Does it conflict with existing constraints? Can theorists explain it without breaking other measurements? These questions may sound cold, but they are the reason physics has earned its trust. And still, after all the caution, the search remains thrilling because the next layer could rewrite familiar words. The word particle might become less fundamental than field. The word mass might become a low-energy effect of symmetry breaking and binding energy. The word force might become a remnant of a unified interaction. The word vacuum might become a phase of fields rather than emptiness. The word matter might become only one visible sector among many. Each revolution in physics changes not just the equations, but the meanings of ordinary words. CERN is often portrayed as a place where scientists smash things to see what falls out. That image is not wrong, but it is too crude. The deeper truth is that CERN creates controlled moments where the vacuum itself is asked to respond. Two protons meet with enormous energy. Their quarks and gluons interact. Fields that are normally quiet can be excited. Heavy particles, if the energy and quantum numbers allow, may appear briefly and decay. The detector does not see the hidden object directly most of the time. It sees tracks, showers, missing momentum, displaced vertices, timing information, and statistical patterns. The event is reconstructed like a crime scene where the culprit vanished almost instantly. ATLAS and CMS are general-purpose detectors built like enormous layered cameras around the collision points. Silicon trackers record charged particle paths. Calorimeters absorb particles and measure their energies. Muon chambers identify particles capable of penetrating the outer layers. Magnetic fields curve charged tracks, revealing momentum and charge. LHCb looks forward along the beam direction, specialized for particles containing beauty and charm quarks. ALICE studies heavy ion collisions, recreating droplets of quark-gluon plasma. Each experiment asks the hidden layer a different kind of question. None has the full language by itself. The data problem is almost as extraordinary as the physics. The LHC produces far more collision information than can be stored. Trigger systems decide in real time which events are worth keeping. Most collisions are discarded immediately because they look ordinary. This creates another subtlety. New physics might hide in signatures that triggers were not designed to preserve. Experiments constantly adapt, adding scouting streams, specialized triggers, and unusual object searches to avoid missing something unexpected. The machine does not merely need power, it needs imagination built into electronics and software. This is why future discoveries may not come from a new energy frontier alone. They may come from better timing, better reconstruction, better machine learning, better theoretical calculations, or better use of old data. The CDFW result came from data collected before the Tevatron shut down, analyzed with years of care. LHCb anomalies shifted when analyses improved. Muon G-2 depends on both new measurement and new theory. At the frontier, old data can become new evidence when the tools sharpen. The hidden layer may already be recorded somewhere, buried in archived events, waiting for the right question. There is a humbling lesson in that possibility. We often imagine discovery as seeing something never seen before. But sometimes discovery is understanding what you already saw. The background becomes signal. The nuisance becomes clue. The correction becomes the point. A decay channel once treated as calibration becomes a window into flavor. A slight mismatch in a mass becomes a test of loop effects. A missing particle becomes a conserved momentum imbalance. The universe does not label its secrets. It mixes them into ordinary data. The strongest conservative interpretation of the current era is that this mixing has not yet produced a decisive signal. The Standard Model has endured the LHC far better than many expected. That fact should be allowed to change the tone. It should make us less sensational. It should make us cautious about claims that a new era has already arrived. But the strongest radical interpretation is that the Standard Model's endurance may itself be telling us the next layer is not where we looked first. It may not be a simple TeV scale extension with spectacular signatures. It may be subtler, darker, more weakly coupled, or more cosmological. This is the mature form of the controversy. The argument is not between believers in progress and defenders of an old theory. It is between two scientifically serious readings of the same evidence. One reading says the lack of discovery is evidence that popular beyond Standard Model expectations were misguided. The other says the unresolved cosmic problems are so large that the lack of easy discovery only deepens the mystery. The first reading protects rigor. The second protects ambition. Physics needs both. Rigor without ambition becomes bookkeeping. Ambition without rigor becomes mythology. A long time from now, the current period may be remembered in one of two ways. It may be remembered as the age when particle physics learned that nature's next layer lies far beyond colliders, forcing a turn toward cosmology, neutrinos, quantum gravity, and precision rather than brute energy. Or it may be remembered as the quiet interval before a hidden sector finally appeared, the way radio silence precedes a faint signal rising from noise. We do not know which story we are living inside. That uncertainty is not a flaw in the narrative. It is the narrative. What we can say is that the next layer, if found, will not erase the Standard Model. It will contain it. General relativity did not make Newton useless. Quantum mechanics did not make chemistry false. A deeper theory of matter will not make electrons vanish or make the Higgs discovery obsolete. It will explain why the Standard Model works, where it stops, and what approximations we were unknowingly making. The old theory becomes a limiting case of the new one. That is how physics usually grows. Not by burning the map, but by drawing the larger continent around it. This matters for how we think about truth in science. A theory can be true within its domain and incomplete beyond it. That is not a contradiction. It is the normal condition of scientific knowledge. The Standard Model is true enough to build detectors, predict cross-sections, guide radiation therapy, model stellar processes, and explain the microstructure of matter. It is incomplete enough that the universe's dominant matter component remains unidentified. Both statements are essential. Remove the first, and you get sensationalism. Remove the second, and you get complacency. There is one more pressure point that rarely fits into public stories because it is not dramatic enough at first glance. The constants themselves. The Standard Model does not predict the electron mass from a deeper principle. It does not predict the muon mass, the tau mass, the quark masses, or the exact mixing angles that govern how quarks change identity through the weak interaction. It accepts them as measured facts. Once those numbers are inserted, the theory becomes extraordinarily predictive, but the numbers themselves arrive from outside the theory like passwords typed into a locked machine. A final theory should in some sense explain why those passwords are what they are. This is not merely aesthetic dissatisfaction. The values of these parameters shape the possible universe. Change the electron mass and atomic sizes shift. Change the up and down quark masses, and the proton-neutron balance changes. Change the strong force, and nuclear stability changes. Change the Higgs vacuum value, and the entire electroweak structure changes. The universe we inhabit depends on a set of numbers whose origin remains mysterious. Some physicists suspect a deeper symmetry fixes them. Others suspect they are environmental outcomes in a larger landscape of possible vacua. Others think the question itself may be poorly framed, but no one can honestly say the standard model explains them. The flavor problem is especially sharp. Why do particles come in families with identical charges but different masses? Why is the muon not just heavier than the electron, but heavier by a very specific factor? Why is the top quark so much heavier than the up quark when both carry the same electric charge and color behavior? The standard model can describe these differences through Yukawa couplings to the Higgs field, but the couplings themselves form a strange hierarchy. To say a particle is heavy because it couples strongly to the Higgs is true, but it moves the deeper question one step back. Why that coupling? Why that pattern? Why this hierarchy rather than another? A hidden layer might answer by making quarks and leptons composite. If electrons or quarks were themselves made of smaller preons, the generations could reflect different bound states. This idea has appeared in many forms, but experiments have found no evidence for compositeness down to extremely small distances. High-energy scattering sees quarks and electrons as point-like within current resolution. That does not prove they are truly point-like forever. It only means that if they have substructure, it must live at distances smaller than we can probe, or be hidden by dynamics we do not yet understand. The idea is constrained, but the question that motivated it has not disappeared. Another possibility is that flavor is governed by a symmetry broken in a hidden sector. The masses and mixings might not be arbitrary at all, but the low-energy shadow of fields whose values set the pattern of Yukawa couplings. In such models, the apparent disorder of particle masses becomes like the apparent disorder of chemistry before the periodic table was understood. A hidden order may exist, but the visible spectrum is distorted by symmetry breaking, energy scales, and mixing. This is a beautiful possibility. It is also difficult to test, which is why it remains more promise than established physics. The danger in all these ideas is that they can seduce us into thinking explanation is the same thing as evidence. A model that explains a pattern is not automatically true. It must predict something measurable, something that could fail. Proton decay, electric dipole moments, rare lepton flavor violating decays, flavor-changing neutral currents, deviations in Higgs couplings, missing energy, long-lived particles, displaced vertices, new resonances, cosmological relics. These are the places where explanation has to risk contact with reality. The hidden layer must eventually touch the detector, the telescope, the underground tank, or the precision clock. Electric dipole moments are a good example of this quiet search. Many new physics models that add CP violation also predict tiny separations of charge inside particles, such as the electron or neutron. The standard model predicts electric dipole moments so small that they are far beyond current detection. If an experiment finds a non-zero value above that background, it would be powerful evidence for new CP violating physics. These experiments do not look like Hollywood particle physics. They use cold molecules, ultra-stable fields, careful control of systematics, and patience. Yet they may probe energy scales far beyond direct colliders, because a tiny forbidden tilt can reveal a very heavy hidden influence. Long-lived particles offer another way the hidden layer might have escaped. Many searches assume new particles decay quickly near the collision point. But if a new particle lives long enough to travel centimeters, meters, or even beyond the detector before decaying, its signature can look unusual. A displaced vertex, a delayed photon, a disappearing track, a particle that stops and decays later. Older triggers and analyses were not always optimized for these possibilities. New LHC searches increasingly target them. This is a reminder that absence depends on the questions asked. A detector can be enormous and still blind to the wrong kind of event if the analysis expects nature to behave conventionally. The hidden layer may also speak through cosmological phase transitions. The Higgs field changed the state of the universe when electroweak symmetry broke. Other hidden fields, if they exist, may have undergone their own phase transitions in the early universe. Some could have produced gravitational waves, topological defects, dark matter relics, or asymmetries between particles and antiparticles. Future gravitational wave observatories may therefore become particle physics experiments in disguise. They may listen not for stars or black holes alone, but for the echo of hidden fields, changing state, when the universe was young. This widens the stage. Particle physics is no longer only the study of small things. It is the study of rules that operate across the smallest and largest scales at once. A field too weak to show itself in a detector may shape galaxy formation. A particle too heavy to produce today may have controlled the matter-antimatter balance in the early universe. A symmetry broken at unreachable energy may determine the masses in your atoms. A vacuum property measured through the Higgs may influence the fate of the cosmos. The hidden layer beneath matter is not beneath in distance alone. It is beneath in explanation. There is another clue in the way discovery has usually happened. The next layer almost never looks necessary to everyone before it appears. Before the electron, atoms could still explain chemistry. Before the nucleus, matter still behaved normally in the laboratory. Before quarks, the particle zoo could be cataloged even if it could not be understood. A working theory can be useful long before it is deep. That is why the standard model's success should not end the search. Success may be exactly what gives us the precision required to see where it stops. The same machine can therefore be both a monument and an interrogation chamber. The LHC confirmed the Higgs mechanism, but it also keeps asking whether that mechanism is lonely. It measures the Higgs coupling to bottom quarks, tau leptons, W bosons, Z bosons, photons, and gluons. It asks whether invisible Higgs decays exist. It asks whether the Higgs can be produced in pairs. Each answer that agrees with the standard model tightens the cage around speculation. Each answer that deviates would point toward a crack in the wall. This is the rhythm of honest frontier science. Tighten the cage, watch the cracks, refuse both despair and hype. The hidden layer may not reveal itself on our schedule, and it may not resemble our favorite equations, but the questions are now too specific to be dismissed as vague curiosity. What is dark matter made of? Why do neutrinos have mass? Why is there matter rather than radiation? Why does the Higgs sit where it sits? Why do 3 generations exist? Why does gravity remain outside the quantum map? These are not decorative mysteries. They are load-bearing gaps in the architecture of our understanding. So the hidden layer beneath matter is not a fantasy added to physics for drama. It is the name we give to the combined pressure of unexplained observations, theoretical structure, and unresolved measurements. It is dark matter pressing on galaxies. It is neutrino mass pressing on the original model. It is baryon asymmetry pressing on CP violation. It is quantum gravity pressing on spacetime. It is the Higgs mass pressing on naturalness. It is precision data pressing on electroweak and flavor calculations. Some of these pressures may be relieved without new accessible particles, but all of them cannot be ignored. So return to the first image, your hand on the table, the world pushing back. That simple sensation contains the entire history of hidden layers. Molecules under skin, atoms under molecules, nuclei under atoms, quarks and gluons under nuclei, fields under particles, and perhaps beneath the fields, another architecture not yet named. The table is real enough to hold your hand. The standard model is real enough to explain why. But reality has never promised that the layer strong enough to support us is the final layer there is. The next revolution may not arrive as thunder. It may arrive as a correction, a mass measured more precisely, a branching ratio refusing to settle, a dark matter interaction barely above background, a neutrino process that should not happen but does, a proton decay event in a tank of silent water. It may arrive so small that only a few people in a control room understand at first what has changed. Then the equations will shift. The old map will remain useful, but a deeper map will be drawn beneath it, and the solid world under your hand will become, once again, less solid and more astonishing than it was the day before. That is the real controversy. Not that physicists have proven a hidden layer. They have not. Not that the standard model is broken beyond repair. It is not. The controversy is that our most successful theory may be showing us both its power and its boundary at the same time. It describes the visible world with breathtaking precision, while the universe quietly points beyond it through darkness, asymmetry, mass, gravity, and faint experimental tensions. The curtain has not opened, but it is not motionless. And beneath everything you see, every atom in your body is waiting for the next layer of reality to be named.